through projects. In this video, we are going to explain about the project title Data Balancing and CNN-based Network Intrusion Detection System Introduction. With the increasing complexity and frequency of cyber attacks, there's a pressing need for automated systems that can effectively filter and classify these attacks. This is crucial to support cybersecurity experts who might otherwise be overwhelmed by the sheer volume of threats. Identifying different types of attacks is vital for implementing specific preventive measures. Understanding the nature and characteristics of each attack type enables tailored and effective security measures to be put in place to mitigate those threats. Numerous machine learning models have been proposed for network intrusion detection (NID) systems. However, their performance can vary due to factors like imbalanced data sets. An imbalanced data set refers to a situation where the distribution of classes, example types of attacks, is not uniform, which can affect the learning process and the accuracy of the models. The project proposes the use of convolutional neural networks (CNN) for classifying different types of network attacks. CNN are a type of deep learning model commonly used for image recognition, but have also shown promise in sequential data processing tasks like time series data or sequences, which can be applicable to network traffic analysis. The performance of the proposed CNN-based system is evaluated and compared to other systems that use various sampling techniques like random oversampling (ROS), synthetic minority oversampling techniques (MOT), adaptive synthetic sampling (ADA-SYN), and data balancing. These techniques are used to handle imbalanced data sets by either oversampling minority classes or undersampling majority classes, aiming to improve model performance. To benchmark the proposed system, the project utilizes the NSL KDD and BOT IoT datasets. These datasets are commonly used in the field of cybersecurity and network intrusion detection for evaluating the performance of detection systems. NSL KDD dataset is a refined version of the KDD Cup 1999 dataset, while BOT IoT dataset contains various types of attacks in Internet of Things IoT environments. Objective: the project's primary aim is to create a network intrusion detection (NID) system capable of effectively handling imbalanced datasets commonly encountered in cybersecurity. These datasets often contain significantly fewer instances of certain attack types compared to others. The proposed system will leverage convolutional neural networks (CNN) as the primary tool for classifying various types of network attacks. The project intends to assess and compare the performance of the developed NID system against other systems that employ different data balancing techniques. These techniques, such as random oversampling (ROS), synthetic minority oversampling techniques (MOT), and adaptive synthetic sampling (ADA-SYN), are used to mitigate imbalanced dataset issues by either oversampling minority classes or creating synthetic instances to balance class distribution. To evaluate and benchmark the performance of the proposed NID system, the project employs two widely used datasets, NSL KDD and BOT IoT. These datasets serve as standardized collections of network traffic data containing various types of attacks. The evaluation includes testing the system's ability to classify attack in both multi-class, multi-attack types, and binary classification tasks, normal versus attack instances. The project places a significant emphasis on ensuring that the developed NID system is not only effective in specific scenarios, but also possesses generalizability and robustness. This is achieved by evaluating its performance on datasets with different probability distributions, such as the NSL KDD training dataset and the BOT IoT dataset, which represent attacks in Internet of Things environments. This assessment helps determine the system's adaptability across varied data distributions and its ability to maintain accuracy in diverse settings. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, Databases SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages into chosen programming language like Python. Packages like Pandas for data manipulation, Matplotlib and Seaborn for visualization, and Keras, a high-level neural network API for building deep learning models, are imported here. Exploring the dataset. This stage involves loading and exploring the dataset. The project involves two datasets, namely NSL KDD and UNSW NB15 BOD IoT. Understanding the structure, features, and characteristics of these datasets is crucial before further processing. NSL KDD dataset is a modified version of the KDD Cup 1999 dataset, specifically designed for network intrusion detection research. It addresses some of the limitations and redundancies found in the original KDD Cup dataset, making it more suitable for modern intrusion detection system evaluation. UNSW NB15, that is BOT IoT dataset, is a network traffic dataset specifically designed for intrusion detection research in Internet of Things IoT environments. It contains traffic data generated in a simulated IoT setting, which includes various attacks and normal activities. Data processing, Pandas data frame. Using Pandas, the dataset is converted into data frame structures for easy manipulation and analysis. Keras data frame, converting data into a format compatible with Keras, which is often a prerequisite for building neural network models. Dropping unwanted column, removing irrelevant or redundant columns that do not contribute to the model's learning or prediction process. Visualization using Seaborn and Matplotlib. Visual exploration of data using Seaborn and Matplotlib libraries. This step includes creating various plots such as histograms, scatter plots, or bar charts to understand data distributions, correlations, and patterns. Label encoding using label encoder. Converting categorical variables into numerical format using techniques like label encoding, especially if the machine learning or deep learning models require numerical inputs. Feature selection. Select percentile using mutual info classify. Selecting the most relevant features from the dataset using a method like select percentile, which uses mutual information classification to rank and select the top features that are most informative for classification tasks. Splitting the data to train and test for deep learning. Dividing the dataset into training and testing sets. This step is crucial for evaluating the model's performance on the data it hasn't seen during training. Commonly, an 80:20 or 70:30 split is used, with the larger portion used for training. Building the model. Constructing the neural network model using the Keras library. This involves defining the architecture, specifying the number of layers, types of layers, activation functions, loss functions, optimizers, and other parameters required to create and compile the neural network model for network intrusion detection. Training the model. This phase involves feeding the pre-processed and balanced dataset into the CNN-based model. Training occurs through an iterative process where the model learns patterns and relationship between features and attack types. The model adjusts its internal parameters to minimize the prediction error using optimization techniques like backpropagation and gradient descent. Flask framework with SQLite for sign up and sign in. Flask, a Python web framework, is integrated with SQLite, a lightweight relational database management system. This combination enables the creation of user authentication functionalities like sign up, user registration, and sign in user login. User data such as username and password is securely stored in the SQLite database. User gives input as feature values. Users interact with the system by providing input, which is in this context refers to feature values related to network traffic. These values include attributes like protocol types, service type, flag, and other characteristics associated with network connections. The given input is pre-processed for prediction. The input provided by the user undergoes pre-processing steps similar to those applied during the initial data processing phase. This includes tasks like converting categorical variables into numerical format, feature scaling, and any other necessary transformations to ensure the input data aligns with what the model expects. Trained model is used for prediction. The pre-processed input is then passed through the trained CNN-based model. The model uses its learned parameters and network architecture to predict the likelihood or classification of the input data as either a normal network activity or a specific type of network attack based on the trained patterns. Final outcome is displayed through front end. The outcome of the prediction, whether it's the classification of the input as normal or an identified attack type, is displayed to the user through the front end. This front end interface provides the user with the system's response to their input and aids in understanding the detected network behavior. Algorithms used to implement this project, we have utilized the following algorithms. The first one is CNN with data balancing. This algorithm involves using a CNN convolutional neural network architecture to classify network traffic data into normal and attack instances while addressing imbalanced data sets. Data balancing techniques like undersampling or oversampling are applied to ensure that the CNN model is trained on a data set with a balanced representation of different attack types, thus improving its ability to learn from minority classes. CNN with ROS, random oversampling. This algorithm utilizes a CNN model trained on a dataset where the minority class, less frequent attacks, is oversampled randomly to achieve a more balanced distribution of classes. ROS, random oversampling, involves creating synthetic instances of minority class data to match the frequency of the majority class, improving the CNN's ability to detect rare attack types. CNN with SMOT, synthetic minority oversampling technique. Similar to ROS, SMOT is a data balancing technique applied to CNN models training dataset. SMOT generates synthetic instances of the minority class by interpolating between existing instances, creating a more balanced dataset and enhancing the CNN model's ability to recognize and classify less prevalent attack types. CNN with ADA-SYN, adaptive synthetic sampling. ADA-SYN is another data balancing technique used in training the CNN model. ADA-SYN generates synthetic instances for the minority class based on their difficulty in learning regions. It focuses on areas where the CNN model will be less effective, further aiding in improving the model's performance on minority class detection. CNN plus LSTM. CNN plus LSTM with data balancing. Combining CNN, convolutional neural network, with LSTM, long short term memory, a type of recurrent neural network for sequence learning. This algorithm addresses imbalanced data sets by using data balancing techniques in the training phase. The combination allows the model to learn both spatial and temporal features from network traffic data while handling class imbalances. CNN plus LSTM with ROS. Similar to the CNN plus LSTM with data balancing, this approach uses ROS, random oversampling, to balance the dataset before training the CNN plus LSTM model. The combination of CNN and LSTM layers along with the balanced dataset enhances the model's ability to detect diverse network intrusions. CNN plus LSTM with SMOT. This algorithm involves applying SMOT to balance the dataset before training the CNN plus LSTM model. By leveraging both CNN and LSTM layers and a balanced dataset, the model becomes more adept at capturing both spatial and temporal patterns in network traffic, especially for less frequent attack types. CNN plus LSTM with ADA-SYN. ADA-SYN is utilized in balancing the dataset for training the CNN plus LSTM model. This method allows the combined model to effectively capture both short-term and long-term dependencies in network traffic data, improving its accuracy in identifying various attack types, including the less prevalent ones. These algorithms represent variations in the approach to using convolutional and recurrent neural network in combination with different data balancing techniques to enhance the performance of network intrusion detection systems in identifying and classifying network attacks. Comparison graphs. Comparison graph offers a visual breakdown of how a model performs across essential evaluation metrics. In this project, we have utilized bot IoT dataset. These are the comparison graphs of bot IoT dataset. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the data set. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Comparison graph of NSL KDD dataset. In this project, we have also utilized NSL KDD dataset. So here, the models are compared with the parameters accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb file. These are Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address. Localhost which is this, and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in. So here we need to enter the username and the password which we have created, and then click on login. We have logged in successfully. So here we need to enter all these parameters to predict whether attack is detected or not. So I'm entering the parameters now. So here we have entered all the parameters. So the first parameter is protocol type. Type of protocol used in network communication, example TCP, UDP, ICMP is 1. Service is 22. Type of service or application involved in network communication. SRC bytes is minus 0.002. Number of bytes transferred in the source and destination directions during a network traffic connection, respectively. Destination bytes is 0.13. That is number of bytes transferred in the destination direction during a network connection. Logged in is 2.39, indicates whether a user has logged in into a service or system during network communication. Count is minus 1.52, total number of observed connections and connections to a specific service, respectively. SRV count is minus 1.15. That is total number of observed connections and connections to a specific service, respectively. SRV different host rate is minus 0.2. Rate of different hosts accessing the same service. Different host count is minus 3.4. Count of connections to the same service from a destination host. DST host SRV count is minus 1.69. Rate of connections to the same service from the destination host. Destination host same service rate is 0.599. Rate of connections to different service from the destination host. Destination host different SRV rate is minus 0.28. Destination host same SRC port rate is minus 1.022. Rate of connections using the same source port from the destination host. Destination host SRV different host rate is minus 0.15. Rate of connections to different hosts using the same service from the destination host. After entering all these parameters, click on predict button. So here we can see we got the result. There is no attack detected and it is normal. Now we will enter another set of parameters and check whether attack is detected or not. So here I'm entering another set of parameters now. So here I have entered another set of parameters. Protocol type is 1. Protocol type indicates the communication protocol used, example TCP, UDP, ICMP within network connections. Service is 45. Service specifies the service or application being accessed or utilized in the network communication. SRC bytes is minus 0.003. It represents the number of bytes sent from the source originating host. DST bytes is minus 0.02, reflects the number of bytes sent to the destination host. Logged in is minus 0.41, indicates whether the user has logged into the system or service. Count is minus 1.5, denotes the frequency or number of occurrences of a specific event or connection. SRV count is minus 1.18, tracks the number of connections to the same service or application. SRV different host rate is minus 0.203 calculates the rate of connections to different hosts for the same service. Different host count is minus 0.84 counts the number of different hosts involved in the connections. DST host SRV count is minus 1.76 tallies the count of connections to the same service by the destination host. DST host same SRV rate is minus 1.8 computes the rate of connections to the same service by the destination host. DST host different SRV rate is 0.08 determines the rate of connections to different services by the destination host. DST host same SRC port rate is minus 1.6 measures the rate of connections using the same source port by the destination host. DST host SRV different host rate is minus 0.15 calculates the rate of different hosts accessing the same service by the destination host. Here, each parameter provides specific insights into network behavior, connection patterns, and communication characteristics, aiding in the detection of potential intrusions or anomalies within the network traffic. After entering all these parameters, click on Predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS, distributed denial of service. Now we will enter another set of parameters and check whether attack is detected or not. So here I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on Predict button. So here we can see we got the result. There is an attack detected. Attack type is probe. Now we will enter another set of parameters. I'm entering the parameters. So here we have entered another set of parameters. Now click on Predict button. So here we can see the result. There is no attack detected and it is normal. In this way, by entering the parameters, we can predict whether attack is detected or not. Now click on Sign Out button. Conclusion of the project. The proposed NID system effectively addresses the challenge of imbalanced datasets commonly encountered in cybersecurity. By utilizing convolutional neural networks CNN, it demonstrates commendable performance in accurately classifying various types of network attacks. The CNN architecture enables the system to learn complex patterns and features from network traffic data, resulting in better identification and classification of different attack types compared to traditional methods. In comparison to other systems employing data balancing techniques such as random oversampling ROS, synthetic minority oversampling techniques SMOT, and adaptive synthetic sampling ADA SYN, the proposed system showcases superior performance. Despite the use of these techniques to mitigate imbalanced dataset in other systems, the CNN-based NID system achieves higher accuracy, better detection rates, or improved classification across different attack categories, indicating its effectiveness in handling imbalanced data. The project assesses the proposed system's performance on datasets with varying probability distributions, such as the NSL KDD training dataset and the BOT IoT dataset. This evaluation examines how well the system generalizes and adapts its learned patterns and detection capabilities to different environment or type of attacks. By demonstrating consistent performance and maintaining accuracy across datasets with diverse characteristics in attack scenarios, the project emphasizes the system's robustness. This robustness is crucial for real-world deployment where the system needs to effectively detect and classify network intrusion across different contexts and threat landscape.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.